Yeah, I'm glad so many people still showed up at the very end of the conference. So yeah, I'm going to be talking about mostly a number of features that were part of the Rust language at some point, but no longer are, and why this is the case, and usually why this is a good thing. So as Ryan said, I'm Marijn Haverbeke. If you are into JavaScript, you might have seen my name before. So Rust has been under development for a while, about 10 years now, I think. First long stretch was just great and working in isolation, and who knows what kind of ideas and experiments he abandoned at that point. There's not even a code repository from that time public, so it's like the prehistory. And then at some point, Mozilla adopted the project and assembled a team. And from a little before that point, we do have Git history, and at that point, everything was discussed in issues and mailing lists, and there's lots of records. I was part of this, pretty much the initial team where we moved from the original OCaml-based compiler to a Rust-based compiler, and we got a bunch more people involved in the language. This was a period of like the first real experience with the language, and a bunch of people from different backgrounds giving their opinions on the language and trying to push it into their favorite direction. And we had a lot of like experiments and dead ends and overhauls and false starts, and just lots of churn. We would sometimes come up with a breaking change in the morning and then have a patch ready in the afternoon and convince someone to merge it later on. And then, because there was only one code base, we just fixed everything right away and people could continue working. There was some trickiness with actually getting like a compiler that compiles the current code after you make a breaking change. So you'd first change the compiler, then upload a snapshot, then change the code, and then everyone could proceed with the new snapshot. And then, of course, a year and a half ago, I think the team cut version 1.0, and then just the process changed entirely. So now it's like everything stays backwards compatible. It's impressive how serious they have been taking backward compatibility. And experiments move, like RFCs move very slowly, and there has to be a wide consensus, and it has to fit within the current code base. So that's a whole different stage again. I'm going to be mostly talking about the period where I was part of the team, which was 2011, 2012, and which was probably the wildest period in terms of features cut, features changed, stuff like that. So it may seem a bit ridiculous that we put so much time into really complicated features just to end up dropping them again. But I think that's kind of an essential part of getting a complex design like a programming language right, that unless you're a super genius, you won't really see in advance what the implications and the interactions between the various parts of the system are. And you have to try it and see how well you can make it work and how well it fits into the system. And sometimes you later have to just abandon it again. I think that's part of a healthy design process for like mere mortals who need to actually see how something works before they can evaluate it. I'm structuring this talk around a number of visions that were part of the language and then dropped again. And I'll try to explain why I think that in every case it was a real good decision to drop them. But it's still interesting to see what the original visions were and what we did end up with. So these are Typestate, a structural type system, and lightweight processes, and finally garbage collection. Let's start with Typestate. Typestate it was actually an important point in initial announcements of the language, and people were very excited about it. What Typestate does is basically allow the compiler to know more about the value than just its type. So an example would be, this is something of type socket, but we also happen to know that it's open, or this is something of type array, but we happen to know, or say vector in the current terminology, we happen to know that it's not empty. something like that, allowing you to add more safety to your program, more static guarantees. So when you're programming, you usually have some mental model of why the thing you are doing right now is valid, is not going to crash. If you're not just making random changes and seeing if the tests pass, you will have some mental model of your program. And to a certain degree, depending on the language, you can tell the compiler about this model, and the compiler can then check whether you are applying your model consistently. So a simple case is just types, that you're actually passing the type that you think you are passing somewhere, and if you don't, then instead of finding out at runtime, you find out at compile time. And this is nice. There's a kind of spectrum. This computer does not have the fonts that my computer had, but imagine arrowheads on both sides. There's a kind of spectrum on which languages fall in terms of how much you can actually communicate to the compiler. So on the one side there's JavaScript. If it's like syntactically correct, okay, let's go ahead, let's run it. And then there's like, on the way other side, there's languages like Coq, which require you to actually construct a formal proof that your program does what it's supposed to do, that it does so in bounded time, in bounded space. Which means you're making a lot less mistakes, but on the other hand, it's like a major project to write a small program in such a language. And there's a reason that not everyone is writing their web servers in Coq or whatever. And Rust kind of falls in the middle. It does have quite a bit of static guarantees, and it helps quite a lot. But it still aims to be ergonomic, like easy to program in, where you don't have to spend too much time working on these things. And one way to see the history of programming languages is kind of one aspect of it, at least, is that we've been finding better and better vocabulary to describe the things we know about our program to the compiler. In a way that's actually convenient. So if you have a really terrible type system, that's often worse than no type system at all. If I have to choose to write something in Java or JavaScript, I'll just take JavaScript, thank you very much. But we're getting better at this, and Rust is making a big contribution here in like bringing a real modern type system to the systems programming space. And the ownership model is, I think, just really, really good. I unfortunately wasn't on the team anymore when this was introduced, so I can't take any credit for it. But I think that is the most exciting part of Rust, and it's exactly this kind of thing where the compiler knows what you're trying to do and tells you when you're violating your model. So back to Typestate. It looked somewhat like this. You could define predicates, which is this pure function not empty at the top. And the extra information that the compiler had about your values came in the form of this predicate holds. But these were actually just predicates written in normal Rust code that they were supposed to be pure. There was a concept of an effect system at that point, which is also gone now. But they just took a value and said, okay, I hold or I don't hold. And then you could define for your functions preconditions and postconditions. So you could say, for example, this function last here demands that its first argument has the not empty predicate holding on it, because you can't take the last element from an empty array. And then before you could pass such a value to such a function, you'd have to convince the compiler that this predicate held at this point. And for some things, this worked relatively well. The compiler was very clever in propagating its information through the control flow graph and like taking it from the post conditions of the functions you called. But here you have an example. For example, I create an array and then I want to pass it to last, but that's not okay. I first have to check that it's not empty. And this is actually a thing, check, would insert a runtime test, a call to the predicate, and then panic if it failed. So But actually, I mean, this array isn't empty. This is very easy to prove, but because the compiler only saw these predicates as like opaque pieces of code, it couldn't actually reason about them. It could only take what you told it. Like if you check, there were variants of check. One of them which just was like an unsafe form of just believe me, this holds. So that might also have been appropriate here because I'm really sure that this array is not empty. And then there was one version that ensured that the compiler already statically knew at this point that something held. So there was kind of an assertion of, okay, I must know this at this point, but don't insert a runtime check. I want to have a static error if it's not provable. But in my experience, the effect of this system was mostly that you would be littering your code with check statements, and they would also panic at runtime. So the amount of static guarantees wasn't very great because usually the compiler couldn't really help a lot with like reasoning about when they actually held and when they didn't. It was in the compiler for a long time still, but eventually it was dropped because it was just not pulling its weight. So in terms of experiments in good expressive ways to express these kind of things, I think this was a failed experiment. It existed in some research languages before, but it's never really made it into a big mainstream type language. For good reason, I think. So much for that. Next topic is structural typing. So in typing systems, you have two concepts where structural typing is, say you have a function type which has a few argument types and a return type, and you want to compare it to another function type. So you're just going to look at the fields in the function. Does it have the same amount of arguments? Are its arguments of compatible types? Is it return type of compatible type? And that's structural. On the other hand, there's nominal typing, where you just say, where is this type declared? What's the name of this type? And it has to be the same. So Rust structs currently work this way, as do enums. Two types are only compatible if they are actual instances of the thing that was declared in the same point in the code. Initially, structs were a structural type, so this curly braces thing there is syntax for a struct type with two fields, x and y of type float. And the type declaration just defines an alias for the type. This is just like a name for the type record with two float fields. And so if I define a function which takes an argument of this point, I can call it with just a record constructed on the fly without any record name involved. Records themselves don't have a name. They just have a structure in this system, and it's kind of nice and lightweight and minimal, and that often you don't even bother to give your record a name if you only use it a few times. So you would now probably use a tuple. You could use a record with nice descriptive field names. I kind of liked it for programming with, but I'll come back later to why this part was removed. Another aspect of this was object types, whereas structure types were only compatible if they had actually the exact same fields and in the same order. They weren't reordered because C compatibility, and they had to be the exact same to be able to compile it efficiently, because then all code that interacted with such a record knew how it was laid out in memory. Objects were a more dynamic feature, and here any object type that has a subset of the fields are always methods, so they're always functions, that this object type has, it's compatible. So I could, if I define a type, a collection of T with these two, this is probably not a very great abstraction, but just bear with me, with a length and an item accessor method, you could take any object that had, I don't know what kind of methods, but also these two, and you could treat it as a collection of T. So these were both the types of the concrete objects and also serve the role of interfaces, which is kind of nice in terms of how many concepts you need to do object-oriented programming. And you could also even use it as a kind of checked duck typing, where you define your function and you just say, I'm only going to call length on the thing that I'm getting. And then anything that had a length method could be passed in. You don't even need to formally define an interface name or anything. It's just all like structural by name. So one implication of this was that because code that used them didn't know their size, they always had to be heap allocated. I think they even always had to be garbage collected. And any calls to them will be going through a dispatch table, a V table. So they're somewhat more heavyweight compared to the rest of the language. And we were finding that in the compiler we were kind of shying away from them unless we absolutely needed polymorphism, because they were more heavyweight than necessary in many situations. And then at some point, well, there was also a lot of machinery involved in actually doing this, like upcasting to a type with less methods, because then you needed to allocate a new V table, preferably statically, which forwarded to the old object and create a wrapper. It was conceptually simple, but not terribly simple to implement. And then at some point, we got more Haskell people on the team, and we all started agitating for a type class kind of implementation interface thing that we ended up now. And because no one really liked these objects very much, we migrated to that. And I think they just fit with the language much better. They don't require you to put something on the heap. They don't require indirect calls unless you actually are using polymorphism. So I think that's a win. But now that we had implementations which affect a specific type, structural records also became problematic, because if you're using a record that happens to have the same shape in two completely independent contexts, and they both define, say, a two-string implementation of it, then these will clash. Even though the actual usages have nothing to do with each other, they will both be trying to implement the same interface, the same trait on it. That doesn't work. So, well, no one cared that much about structural records either, so they became nominal for this reason at that point. Now, of course, tuples and functions are still structural. They don't make much sense in any other way, but the like heavy emphasis on structural typing was abandoned. Again, for good reasons. Then, we saw a talk about asynchronous and versus synchronous programming yesterday, and there are languages like Go and Erlang which kind of solve this in a different way, where your programs look like they're synchronous, but that's just like a sleight of hand. And well, no, they are actually programmed synchronously, but you don't pay for I don't know how many threads, because they have their own process abstraction, which is much more lightweight than operating system threads. That was part of Rust's initial vision, so you don't need to mess with futures or reactors or anything. You just spawn a bunch of tasks, which, for example, for each socket, or you could even, if you are writing a calendar, spawn a task for each task on the calendar or something. And they run as independent processes, but because they're like designed to be cheap, you don't have to worry about allocating millions of them. It just works. Now, operating systems aren't really designed with this in mind. They come from a period where people were not considering millions of threads a reasonable thing to do. And usually their internal data structures, as well as the minimal overhead they impose on a thread, is just too much to use operating system threads to model, say, every socket on your web server. So what you have to do then is you create your own thread pool in the language runtime, and you have your own task abstraction, and your threads are kind of just picking up tasks, running them for a while, and then when they block or when their time runs out, they put them aside again and they take another task. You do your own scheduling, which is also not trivial. And of course, even if you do this, you still have the problem that simple machine code has this conception of a stack, where it can allocate stuff in a last in, first out manner, where it grows during function calls and shrinks again when you return. And that kind of depends on a conceptually infinite stack being there, where you can just always take memory. Now, they're not actually infinite, of course, but they're usually big enough to allow reasonably recursive programs to run without overflowing your stack. But that means big enough is quite a bit. You're going to not want your minimum stack to be half a kilobyte, because then every program will overflow it. So we got away from this simple stack model and introduced segmented stacks, which are stacks where each function that wants to actually allocate on the stack first checks whether there is enough stack. And if there's not enough stack, it allocates a new piece of stack and kind of links that to the current stack and continues running on that. And then when that function returns, it'll throw away this piece of stack and return to its old stack. Oh, that's not good. Can you give me a cable? Oh, got one. I hope there's a power thing here. There we go. The reason we don't just grow the stack and copy the old stuff onto the new stack is that would involve moving values in memory, and that's a whole different can of worms. Then all the code has to actually be able to locate every pointer to rewrite it, and if the pointer is held by some C code, then who knows where it should be rewritten. So that's why we actually preserve the old piece of stack and then continue on a new piece. That worked actually. It's quite a magic trick, but it worked. It ran for a while in this way, but it does have some drawbacks. The biggest one is that if you have an inner loop which is going to be running very often, and that is exactly at the point where you're crossing to a new stack segment, it's going to be allocating and throwing away so many stack segments that some of our benchmarks, I think it happened only once with our benchmarks, but it was just suddenly ridiculously slow, exactly because of this. The stack switch happened exactly at the part of the benchmark that was running millions of times. So that's not a great abstraction. It's kind of leaky. It also has issues if you're going to call C code. The C code won't be managing segmented stacks, so you have to provide it with a big stack. So we had a pool of big stacks, and whenever you made a foreign call, you'd get a big stack and then call on that stack. There's lots of complexity there. Same if you want to call Rust code from C, you also have to arrange for the stacks to be in the right shape. It worked, but it wasn't great. And so this whole ambition was just given up in terms of we don't want to pay that much runtime library complexity. We don't have all these problems with our own stack model, as well as all the checks that are inserted in the code to make sure that there's enough stack whenever we allocate anything there. And there the call was made to just not do that, so that we could be the kind of language that you can just link into a C program without pulling in I don't know what kind of abstractions and problematic factors. The kind of thing that you can write an operating system in, that would also be a lot more challenging if the language depended on a big runtime. So no Go lightweight threads, and it's cool to see the kind of solutions that are being found as in Tokyo and these kind of cheap futures. The next one is kind of a similar story. So we started out with garbage collection because most of us were coming from garbage collected languages as a kind of, in terms of, okay, this is what a good language looks like. And we felt that you can't really provide an ergonomic language if you don't provide garbage collection. We did have a model where, of course, you only used garbage collection when you wanted. Like it was opt-in. Most values would be on the stack, and you could like have, I think they were called unique pointers at the time, where you would just what the box does now, and you could write whole programs without ever using garbage collector, but there was one. It was at the time a reference counted garbage collector with like a cycle breaker that would run now and then. But there were plans to make it like a more modern style of garbage collector. But again, this has a cost. This is a bunch of runtime complexity that you're pulling in. You have to deal with like, what if C code gets a hold of such a pointer? How do you know that we can't garbage collect it? So again, the complexity was deemed too much. Actually, this was quite a while after I left. Then Patrick Walton announced this plan, like, hey, we could just get rid of the garbage collector. And my initial reaction was, no, that's ridiculous. But then he explained, like, and it finally clicked for me that we could really be in the same niche as C++ is, which is, I think, the hugest thing, is the reason why Rust is at all successful, because it can be this like almost runtimeless language without any complex machinery around it. So it's kind of capitulating to the simple-minded programming model that we've been using for ages as a kind of baseline, which is a shame in a way, because it's not perfect, but it's for systems programming, it's the best we have, and allowing this language to just be dropped in where you would normally use C++ is probably its biggest selling point. So then I kind of got it, and it was like, okay, this is a future that I can be excited about. And I think it was actually relatively painless, because you can just swap in a reference counted pointer, and have to be a bit more careful about cycles, and that's all. So there's still research work being done about integrating with garbage collectors and other systems, but I don't think that's moving that well. And I don't know, I think we landed on a really good place here in terms of how bare bones the language should be. Yeah, this was an example from the book that I wanted to show. It's not entirely painless not having a garbage collector. Returning a closure looks like this, and it's not exactly Haskell, but yeah, okay. I mean, it's a compromise we have to make, and I think it's worth it. Yeah, thanks for listening. I think we still have time for a few questions. So yeah, let's hear them.
We have 2 minutes for questions, so does anybody have a question? I saw your hand in the back first.
Not that I would encourage someone to do that, but wouldn't the structural type kind of thing work like a template or like a generic would work? That you could like generate a specific implementation for a certain type and then work without a vtable?
Yes, you can actually, and I think LLVM was in some cases clever enough to just do this for us, where it would see that it was always the same vtable and it would just inline it. But you're still kind of paying a conceptual cost for it, and I think it's easier to just have a model where you don't generate this complex code and then optimize it back to one where you actually rely on these kind of clever optimization tricks.
All right, one more question. I saw you.
Hi, so recently I saw it was either an RFC or a Rust internals thread, where someone was proposing also this these anonymous structs like you had in your slide. Okay. So you didn't really touch that much on why they were removed. I'm just curious what your opinion is on like whether that would be a good thing to re-add into the language, because my personal opinion on it is fairly favorable, and I think it would be a good idea.
The main reason, as I remember it, for removing them, or at least like at that point, I think we saw it as, do we make the structs we have nominal or structural? And the reason for moving to nominal was that they just work terribly with traits. You can't have this, what's called coherency, where you guarantee that you, even if you link multiple modules together, you don't end up with multiple implementations of the same trait for the same type. And that's kind of important to have, so that was the reason for that.
But I mean, we do have like now we can sort of make trait implementations for like these large tuples, although it's not generic over integers yet.
Yeah, but you have to do that in the trait that defines the trait. You can't do it anywhere else. Yeah, and that's the restriction that it could work. Of course, you would wrap your structs in some other type and then define it on that. If you really need to define a trait in a different trait, it's not very easy or convenient.
Thank you.
Right. Unfortunately, we're out of time for questions.
All right. Thanks.
But I'm sure there will be some time afterwards. So now, one last round of applause, please.